Hi, this is June, and I'm gonna talk about some examples of how calculus is used in real life. Since we are CBT students, I brought something related to what we've learned and what we're gonna use and learn next semester. As Stephen says, calculus is used a lot in our subjects. For example, first and second moment of area, analyzing structural behaviors for beams, columns, and even fluid and soil as well. But today I'm gonna talk about second moment of area, which we're gonna use a lot in strength of material next semester. So this is what I'm gonna do. So firstly, I'm going to introduce second moment of area and definition, and lastly, we're gonna try example problem. So before we get into this, let me ask you guys a question. If two wooden beams are subject to load 100 kilogram, which beam causes more bending? Please note that these beams are made of same material and the loads are applied at the center of the beam. Seems pretty easy. Okay, let me try with another question. Now you're gonna break a ruler by bending each end. And which way is easier for you to break the ruler? I guess you already know the answer because you just try and see which one is easy immediately, right? But why? Why a section with longer edge has more resistance to bending? It's because the section has bigger second moment of area than the one with shorter edge. So therefore, basically, the second moment of area is a structural property that tells you how much resistance a section has for bending. And it is determined by a geometric property of the section, such as rectangular, triangle, circle, or even complex shape. So this is the definition of second moment of area. So here, Ix means second moment of area about the x-axis. So like if the load is applied at the top of the beam, this beam is bent about the x-axis. And y is distance from centroid to a segment of the beam, a segment of the section. And dA is area of the small segment. Okay, so now let's calculate the second moment of area for a rectangular section. So this is typical rectangular section where its width is b and height is h. So you set the formula, and in this case, dA can be substituted b times dy. And you keep solving these problems, and you end up getting bh cubed over 12. So second moment of area about x-axis for this rectangular section is bh cubed over 12. So I told you the greater second moment of area is, the greater resistance a section has for bending. And since it is proportional to h cubed, its value rapidly increases if you increase the height of the section. Okay, and let's try this circular section as well. It's basically the same principle as rectangular section, and you just keep calculating this value and you end up getting pi r to the fourth power over 4. Okay, let's try this example problem here. So firstly, calculate second moment of area of beams below. So those are beam sections given. Um, it's all same but different sections. And find out which section has the highest resistance to bending. And also find out which section has the most efficient resistance for the amount of material used. So it means like a cost efficiency, right? And this is assumption. Assume these beams are made of same materials and subject to same load. Means same condition. So we already know how to calculate the second moment of area for circle, rectangular sections. So I already made a calculation here. And this is summary. So firstly, rectangular section has the highest second moment of area value. Yeah, obviously the rectangular section has the highest second moment of area value. However, W flange has the most efficient resistance for the amount of material used. So circle, square, rectangular area is 0.5, but wide flange is only 0.2, which is less than half the value of everything else. But its second moment of area value is greater than circle and square. That's why the wide flange is widely used as a flexural member, because it is cost efficient and still has a good value for second moment of area. Okay, so that's all for my presentation, and I'm gonna wrap up today. So thank you for listening. Bye.